All right, so let's get started with the reminders here. So homework 1 was due last night. Okay, so and then 2 is up now online. It's due next Thursday. Then 3 will be due. It's not up, but it will be due 1 week after next homework is due. Okay, and then on Monday, that's when we'll have our first exam for the class. Okay. Just keep in mind in on expert TA, typically there are 10 questions posted. You don't have to finish the previous one. If you got stuck on number 2, you can always go ahead and do number 3. Okay, just in case if you don't know that, but that's something you may want to keep in mind. Let me see. I think I have posted solutions up here already. So for number 1, the solutions, they are here. Okay, you can go and then take a look if you didn't know what, like you didn't know maybe some of the problems you didn't know how to solve. The solutions here. Okay. All right. So we'll then. Oh, then for the classroom disinfection for today, Jeffrey and Luke. Okay, after the class. So last time we talked about sound. Sound is a wave, and then hearing is the perception of the sound. And because it's a wave, you can use the quantities, like these quantities to describe its frequency, speed of wave, etc., period, and wavelength. Okay. And then speed of sound is different in different materials. Also, it's dependent of temperature in the same materials. Okay. For temperature dependent, it's proportional to square root of the temperature. Okay, so then that's the summary of the left page. Intensity, sound intensity. So it's defined by the energy of the sound, which is a wave. Wave should carry energy. Okay, divided by area, divided by time t. And then energy divided by t is power. So then it's also equal to power divided by area. If it's a point source, then it's equal to power divided by 4 pi r squared. In that fashion, this the sound propagate in all directions, so then it's in the spherical at a particular location r. Sound intensity then can be calculated from the intensity of the sound, which is a logarithm function over there. The beta equal to 10 dB logarithm of I over I naught. I know it's the threshold that we could hear with our ears. Today we are going to take a look on another factor of the sound wave. So although we are talking about this with sound wave, but this can be applied to other waves as well. Okay, so like for example, microwave or etc. Okay, other stuff. So this is called Doppler effect. This is when you have either the source or the observer of the receiver, we can put that way, is moving, or both of them are moving. So then the pitch or the frequency that you heard is different from it's given out at the source. Okay, so there's a frequency change if either the observer or the source is moving, or both of them are moving. Okay, like when if you are standing on the roadside, if a car drives by you, then you can hear the change in pitch when it's approaching you, and then after it's moving away from you, right? So that's something you guys probably know already. So basically, this is what's happening. So we'll take a look on the case that if the source is moving, all right, and if the receiver is stationary, so say the receiver is over here, the source is moving towards the receiver in this time, in the figure here on the left, okay, and then on the right is the I'll just zoom into there for that case. Okay, so you can see then the first wave gives out by the source. Okay, we will have a wave peak that is approaching the receiver, okay? And then certain time later, a time T2, it's actually closer to the observer. So then the wave peak that gives out at that moment, okay, will take shorter distance to reach the receiver, right? So in that case, you can see the time it takes for the receiver to hear the sound wave is changing, it's getting smaller. So then that means the frequency, that how frequent the receiver hears the sound is increased, right? So there's a frequency change there, right? Or if you look at like um, how far that the wave have to travel to reach the receiver, then the distance travel will become smaller, okay? And then in the unit of one wavelength, it's actually getting smaller if um, um, the source is approaching the receiver, okay? So in that case, you will take the minus sign in this equation. So it can be expressed by this guy here. And then the plus sign is referred to if the source is moving away from the receiver, okay? So in that case, the distance for the wave to reach the receiver becomes longer, so then you add it up, okay? And in terms of frequency, so this is in terms of the period. In terms of frequency, this is how it is, because frequency is 1 over the period. Okay, so V, in this case, the V is the speed of the sound, all right? And U sub S, okay, is the speed of the source is moving. Okay, so the two speeds are here. All right, speed of sound for V, U sub S is the speed of the source that is moving, all right? And T is the period, and then F is the frequency, okay? Now, as I mentioned, the frequency will change. So then if you look at the frequency heard by the observer or the receiver in this case, either way, if you put as receiver, then you can write F sub R. But in this case, we are talking about F sub O, which means observer, is equal to the new wavelength divided by the speed of sound divided by the new wavelength, okay? And then after you plug in this guy into here in the place of lambda, you figure that it's equal to this guy or equal to this guy, okay? This expression here. So F sub S is this frequency that is given out by the source, all right? If you are looking for frequency received can be either expression. You can use this one or you can this one. Okay, so and this one, it takes into account the ratio of the speed of the source divided by the speed of the sound. Okay, so typically the speed of sound will be just the speed of sound in air. Okay, for a lot of cases that we'll be talking about in this class. So then this is fixed, like the 343 meters per second, or a lot of times we can use 340 meters per second. All right. US is again the speed of the source. FS is the frequency given by the source. Okay. We will take a look on one exercise here. This says the bat, which is moving at a speed of 3.25 meters and emitting sound of 35.0 kilohertz, approaches a moth at rest. Okay, so in this case, the moth is the receiver, because it's asking what frequency is heard by the moth. Okay, so the moth is stationary, it's the stationary observer or receiver. The bat is the moving source. All right, so what will be the new frequency that's heard by the moth? And then B, if the speed of bat is increased, is the frequency heard by the moth higher or lower? Calculate the frequency heard by the moth if the speed changes to 4.25 meters per second. Use the speed of sound as 340 meters per second, okay? So you have to determine if you want to take the plus sign or minus sign here. Okay. All right, so many of you guys have your responses in here. So in this case, the source in the bed is approaching the mouse. Okay, so the source is moving towards. So you're picking negative sign here. Okay, so the negative sign is what you want. So then F0 is equal to 1/1 minus US is the speed of the source, okay, being 3.25 meters per second divided by 340 meters per second, okay, multiplied by 30.0 kilohertz, okay, that will give you about 35.3 kilohertz, okay, and in the case that if the speed of the bed is increased, so then this goes up, right? So the whole thing here in the fraction here goes up, but 1 minus that will go down. The denominator goes down, so that means this will go up again. So you guys got that right. So it should be increase. Okay, it will increase or increases. And you can calculate quantitatively, just plug in the new numbers, right? 1 minus 4.25 meters per second, 340 meters per second, okay? And times 35.0 kilohertz, okay? That will give you 35.4 kilohertz, okay? All right, and then for you guys that submitted your responses, I think you all got this right, okay? All right, let me know if you have questions on this before we move on. All right. So if not, then let's check on another scenario that when the source is stationary, but the observer is moving, okay, in that case. Now we'll take a look on the case that observer is moving towards the source, okay. So in that case, then you can see for different peaks. So let's say the line here is the peak, in between the line and the middle is the valley, okay, where you will hear minimum. But when the observer hears the maximum here, if observer is approaching it, right, then he will hear the peak that is more frequent, right, than his stationary, okay. So in this case, you can see if the observer moves towards the source, then the frequency will increase, all right. Now, as I mentioned earlier, this not only just happened to the sound wave, but also happens to other waves. So in astronomy, this is used very heavily. Like you can determine what's the speed of say a galaxy that is moving away from us. Okay, so you're actually looking at the light it emits and then see the frequency change of it. Okay, so that's either called if galaxy is moving towards us, then you will have the blue shift in frequency. Okay, it's called blue shift. Otherwise, it's red shift. It's going away in that sense. Okay, so similar to this. And this is what happens. So, or if you look at the distance that is needed for the wave to propagate from wave peak to reach the observer from one peak to the next one. Okay, so for this peak, if this is stationary, then it takes the lambda, right, from here to reach the observer. But if the observer moves towards it, then it only takes from here to here, which is less distance, right? So that's consistent with the frequency change as well. If you put that into equation, then this is the new frequency you get. Okay, so F0 equal to 1, either plus or minus mu0 divided by, or mu sub O divided by V times Fs. Now, mu sub O is the speed for the observer, because in this case, the observer is moving. Okay, V again is the speed of the sound. If you are approaching the source, then frequency gets higher, so you take a plus sign. Okay, if observer is approaching the source, you take positive sign. If the observer is moving away from the source, then you take negative sign. Okay, and then this frequency will decrease in that case. Okay. All right. So on this one, let's take a look on this example here. It says when the bell in a clock tower rings with a sound of 475 hertz, a pigeon roosting in the belfry flies directly away from the bell. If the pigeon hears a frequency of 448 hertz, what's its speed? Again, use the speed of sound as 340 meters per second. Now you are going to use the formula we just learned in the previous slide, okay? So you're going to use FO equals to 1 plus or minus U sub O over V times Fs. All right. So let's take a look here. So it says the pigeon flies away, right? So in that case, the frequency heard will be becoming smaller. So again, you'll take a negative sign here in this case. All right. So the negative sign is what you want. Then you are given the frequency heard by the pigeon, and then the frequency gives out from the bell, and this is the speed of the sound. So you're looking for the speed of the observer here in this case. Okay, so you're going to set that up 448 hertz equals to 1 minus u of 0 divided by 340 meters per second times this 475 hertz. Okay. Then you are going to divide both sides by 475 hertz here. And let's see. So then that equals to that guy. So that means you can move this to the other side. So 448 divided by 475 minus 1 then equal to minus of mu 0, mu o, 340 meters per second. Okay. Now multiply both sides by minus 340. Will give you the answer you want for your U0, right? So U0 is equal to, in that case, is equal to 19.3 meters per second. Okay. All right. Again, let me know if you have questions before we move on here. All right. Now, a lot of cases, you would have the source is moving, and then at the same time, your observer is moving as well. Okay. So in that case, then you'll have to combine the both factors here, but you can actually combine them into one equation here. So this is the model of the general equation you could write for the case of if both of the receiver and the source are moving, or maybe you can apply to like any of just in general case. So for example, if you just have the receiver is moving, so then you only have mu of 0, all right? You wouldn't have mu of s, because then the source would have speed of 0, okay? So that can be included in this equation as well, okay? On the other hand, if you have just source is moving, then this is not 0, but then observer will be 0, okay? Then it kind of recover what we had before, okay? So pretty much will be the same. So this is a more general equation, just one equation to describe all the scenarios, okay? Yes. Right, so it depends. So you will just have to see if, say, the observer is moving away, right? So then you expect the frequency to be decreased. So then you'll take the negative sign here on the top here. Then you have to, again, judge like for the source, if source is moving at all or not. And then if it's moving towards the observer away. Okay, if it's towards the observer, then you take the minus because it's in the denominator here. Okay, if it's away from the, if it's away from the observer, then you take the let me see, yeah, take the plus, because then we'll make the frequency smaller. Okay, so always the case, if you are getting closer, like the sources towards the observer, then frequency will increase. Okay, otherwise, if they are away from each other, then will decrease. All right, we can take a look on one example, so then we can know what signs to pick. Okay, so as usual, I have you guys try this first, and then we can take a look on the solution together. So this one says a motorcycle and a police car are moving towards one another. The police car emits sound with a frequency of 523 Hertz and has a speed of 32.3 meters per second. The motorcycle has a speed of 14.8 meters per second. What frequency does the motorcyclist hear? Okay. Now you can use that general expression here, and then you are going to decide what sign you want to take, both for the numerator and denominator. All right, so I think I saw several responses in here. We can take a look here. So because they are approaching towards each other, right? So then for the observer here on the top here, because it's approaching the source, so then the frequency you will expect to increase. So then you're going to take the positive sign, right? Now for the source down here, it's approaching the observer, so you will expect the frequency to be going up as well, okay? So then you need to take the negative sign at the bottom here, okay? So that frequency will increase. So basically then this becomes V plus U0 divided by V minus US, okay? Times Fs, okay? Then you put in your numbers here, 340 plus 14.8 divided by 340 minus 32.2, okay? They are the same units of meters per second, so we can just leave out the units there. Let me just stop sharing. You can see a larger view here. Times the speed, the frequency by the source 523 hertz, okay? That gives you 603, all right? That's the frequency heard by the motorcyclist. Um, so if you are wondering, so the application of the Doppler's effect in our daily life. So if you ever had the trouble of speeding and then being stopped by a police car, so they use this technique, okay? So Doppler's effect. So basically the detector gives out frequency, and then when it gets back from your car, they can detect like what's the speed of your car, okay? So that's it. That's this over here. All right. So let me know if you have questions before we move on. Okay. So you can see that, let me see. You can see mathematically, let me show you on the equation over here, okay? So if the source is going to be approaching the observer, so then you are looking at this equation over here, but then in the denominator here, you'll take the minus sign, or starting from here, you will have minus sign, right? So then frequency equals to v plus u0 or minus whatever, but at the bottom here is v minus us, right? Times fs. So then as you can see, if the observer is approaching with the speed that is close to this guy, right? If this is approaching close to the 430 meters per second, then you can see this becomes very smaller, all right? Denominator becomes very smaller. So then on the plot here, you'll see that then there will be a dramatically change in frequency heard by the receiver when the speed of the source is approaching the speed of the sound, right? So it goes up like that, right? On the other hand, when observer is moving with the speed of say whatever u it is, even it's close to the speed of sound, it doesn't get the same effect as the source is moving, right? So when this happens, it's called this sonic boom, okay, will be created. So basically, yeah, approaching very close to the speed of sound. So in some cases, the source might be traveling more faster than the sound. Okay. So for example, for a supersonic airplane to go beyond the speed of the sound, then the wave goes out actually. So you'll see that the airplane first, and then the wave it emit is behind it. Okay, so it's actually traveling less as faster as the airplane itself. Okay, so we'll take a look on a video here to see an example on that. But let me stop sharing and then reshare. Let
Here. Ever since humans invented the wheel, we have been obsessed with speed. For thousands of years we have been designing and engineering vehicles and techniques to help us move faster. We eventually invented the car, which allows us to travel anywhere at speeds of up to a few hundred kilometers per hour. We then quickly realized that this was a grave mistake, because all it did was allow us to get to work faster. So we invented even faster aeroplanes, so we can instead go sit on a sunny beach somewhere sipping a pina colada. But this incessant pursuit of speed has come with some strange side effects, namely the sonic boom. At sea level, sound travels at 340.29 meters per second, which is pretty darn fast. But in 1947, some bloke called Chuck Yeager, who was an American test pilot and speed-obsessed lunatic, managed to travel faster than that, at 428 meters per second, and break the sound barrier for the very first time, using a Bell X-1 aircraft. Witnesses heard an extremely loud boom and saw something quite strange, a cone-like object emanating from the aircraft. This will come to be known as the sonic boom. But what is a sonic boom, and what causes it? Let's find out. Sound travels as a wave, with crests and troughs. If you were to visualize sound waves, they would look like spheres emanating from the source of the sound, with each ring representing a crest of the sound wave. The crests of the sound wave appear almost perfectly symmetrical when the object emitting the sound is stationary. However, when it starts to move, something peculiar happens. The spherical sound wave crests that are travelling in the same direction as the object get squashed together, and each wave reaches the observer quicker than the previous wave. Yeah, I know that can be a bit tricky to wrap your head around, but basically, when an object moves, sound gets squashed. The result of this sound wave compression is an increase in the frequency of the sound. This means the sound becomes higher pitched as the object comes closer to you. This is why cars approaching you sound higher pitched than when they're driving away from you. Think of it like putting a big burly bloke on a fast roller coaster. His voice may sound deep and full of confidence when he straps himself into that seat, but start that baby up and he starts squealing like a little kid. Okay, that's not totally caused by sound wave compression, more a general dislike for roller coasters, but you get the point. On the flip side, however, wave crests that are being emitted in the opposite direction to which the object is travelling take longer to reach your ears, so you hear the noise at a lower pitch. This is known as the Doppler effect. But why on earth am I telling you about all of this? How does it relate to a sonic boom? Well, it's extremely important to understand the Doppler effect, because a sonic boom is created by exploiting the Doppler effect. Take a high-speed aircraft, for example. As it travels through the air, it is constantly emitting sound waves. Just like any other sound-emitting object, these waves radiate from the source in a spherical fashion. The sound coming from a jet is mostly a mix of engine noise and air resistance as it pushes air molecules out of the way at very high speeds. The latter is what is responsible for that whooshing sound you hear as an aircraft passes overhead. The sound waves being emitted in front of the aircraft are being compressed. The faster the aircraft is travelling, the closer together these waves get. But as long as the vehicle's velocity is not higher than 340.29 meters per second, that's the speed of sound, the waves will never touch each other or overlap, because each wave is travelling fast enough so it can get out of the way before the next wave is emitted. But what happens when you travel faster than the speed of sound, and don't allow each wave enough time to propagate outwards before the next wave is emitted? This is where things start to get funky. When the aircraft exceeds the speed of sound, each sound wave is released ahead of the previous wave, because the object that is emitting the waves is travelling faster than the waves themselves. This causes the waves to get pushed together and create a single sound wave with an enormous amount of energy called a shock wave. If we could see this effect in real life, the sound waves would appear as a cone trailing behind the aircraft. This is known as a Mach cone. In the field of aeronautics, the speed at which sound travels is known as Mach 1. The result of this extreme compression of sound waves is a very deep audible boom, which we refer to as a sonic boom. Any observer watching the aircraft pass by wouldn't actually hear the sonic boom until the very tail of the Mach cone reaches their ears. However, the pilot, as well as any passengers aboard the aircraft, wouldn't hear the sonic boom at all, because they are travelling faster than the actual sound of the boom. So the sound will never catch up to the aircraft and will never reach their ears. They can sit comfortably in their cabins, sitting lattes whilst travelling faster than the speed of sound in relative silence, unbeknown to the fact that they're deafening every poor sod that they pass below. Contrary to popular belief, a sonic boom doesn't just happen once as an object breaks the sound barrier. The Mach cone and the sound of the sonic boom are present for the entire time that the object is travelling faster than the speed of sound. For as long as the aircraft is travelling at this speed, the boom remains a constant noise that follows the aircraft around. So that explains the sound. But what about the visual effect of a sonic boom? What causes that weird cone-shaped object to appear behind the aircraft when it breaks the sound barrier? This is caused by a rapid change in air pressure, which is caused by the high velocity of the aircraft. This drop in air pressure causes the temperature in the atmosphere behind the aircraft to drop significantly, causing condensation in the air. So what you're actually seeing is water vapour in the air undergoing rapid condensation. But this is not actually directly related to breaking the sound barrier. Condensation clouds from aircraft can be seen at a whole range of velocities. These condensation clouds don't always coincide with a sonic boom. Whether you see this phenomenon or not depends on many factors, such as the humidity of the atmosphere and the air temperature. It's not just high-speed aircraft that can produce sonic booms though. Sonic booms are found in many places in both nature and the man-made world. When you crack a bullwhip, the cracking sound is not caused by the whip hitting itself. The noise you hear is actually a tiny sonic boom, created as the velocity of the whip surpasses the sound barrier. The pistol shrimp is also capable of creating a sonic boom. This tiny little bugger is like the Chuck Norris of the ocean. It can snap its claws together so fast that it creates a sonic boom between its claws. This sound is so loud that it can stun or even kill other sea creatures. That's basically like being able to kill someone by clapping your hands. For goodness sake, nature, calm down. That's just a ridiculous amount of power to give to a shrimp. But it does go to show, anything we can do with technology, nature has probably already beaten us to it. Thanks for the view, subscribe for more 42.
Alright, we will stop here then.